In the following, we will see some of the building blocks that we can use to construct our networks. So these are these layers, and here I'm printing the number of layers that were available when I prepared the course for PyTorch, and most of them will be available, or I would say all of them will be available in most libraries. And actually the networks are constructed by adding these layers into specific orders. So let's see each one of the layers independently. In this first video we will see the simple ones. So the simple ones are dense layer, linear layer, convolutional, and the pooling layers. So let's see each one of those. So let's say that the first one is the fully connected network. So the fully connected layer is also called a dense layer. So these dense layers, they have a number of inputs in the input at the input of the layer, and they will produce a number of outputs in the at the output of the layer. So the layer is just this one. So here we would have multiple layers, one layer, two layers, three layers. So each one of these layers is a dense layer. So the number of inputs, so let's say that the image has, so the input is an image, and the image has a size 512 pixels, so that is 512 squared, and then there is a bias. So there is a bias that is an extra input to the network. So it is 512 squared plus 1. And then let's say that the output has n1 output features. So output numbers. So the number of parameters for the full dense layer is this number. So it is 260,000 times m1. Each one of these nodes needs 260,000 different numbers. So you can imagine that for 512 images, this can be a huge amount of numbers. This is 10 to the 5, and if you want to produce another image of the same size, then you would need 10 to the 10 coefficients just for a single layer. So this we will simplify later with convolutional networks, in which all these weights are shared between pixels, so that we don't have to specify 10 to the 5 or 10 to the 10 weights, but we can specify many less. So these are dense layers. Dense layers are typically the ones that you find towards the end of the network. So typically you start with your images or your volumes or whatever at the input. They have a very high dimensional density. Through the network, you condense that information into an information bottleneck, and then that information bottleneck somehow is used. Typically it is called a latent space. So that vector in the latent space is used to produce a useful output, and this connection from latent to useful output, very often they are done with dense layers. So dense layers and linear layers, they are somehow almost the same, except for the activation function. So actually you might there might be situations in which you don't want to do anything to the input data, so you have this identity linear layer, or you have the linear, bilinear, lazy linear. So the difference is which formula you are applying. So linear, you have an input data, and then you're multiplying by a matrix and adding some constant. Here in the bilinear you have two input data. So what you do is x1 transpose a x2 plus the bias. So actually the difference between a linear layer and a neural network is somehow represented here. It is also the same relationship that we have between linear regression and non-linear regression. So in linear regression, what we are doing is we have a set of data, you multiply by a matrix, this W transpose. Here it is the same, so it depends on whether your input data is a column vector or a row vector, so it is the same idea. So you multiply by a matrix and then you add some bias. This would be linear regression. In the neural networks, the dense layer would be doing the same, but then going through this non-linear activation function, and then this is the input. So this first layer would be this operation here would be the output here, and then you are computing your final sample or your final output. The final output is the input of this one, the input multiplied by a second matrix, this W2 transpose, plus some bias coming from this node. So here we have the formula for two-layer regression, but my message here is linear layers and dense layers, they are almost the same except for this non-linear activation function. Good. Then some more ideas about how the different dimensions are handled. So here it is somehow it is using a convolutional layer that we have not seen yet, but somehow it represents well the idea I want to convey. The thing is that the input to the layers will be tensors, and these tensors will have a given set of dimensions. Then your kernels and the operations that you do, they also have some tensors, so they are also specified by tensors, and these tensors will have some sizes. And then the output will also be a tensor, and they will also have their own size. So here the input tensor is h times w times 3, because we have 3 channels, so let's say that we are working with color images. And then in this output tensor we are producing h prime, w prime, so they are still images, but now for us we will interpret them as 10 channels, so that are somehow 10 features, non-linear features that we have computed from the input images. And then what are the sizes of the bias? So for instance, this output here will have this number of batches, then number of channels out, and the size of the channels out is defined somehow by the size of these inputs. So somehow this is just schematizing, adding a schema of how the data will behave, how it will be treated. But it is not an actual representation of the sizes of the output tensors. The sizes of the output tensors depend on what is the size of the input tensor. Okay, but then in these operations you have, for instance, to add a bias, but because your output is of size 10, your bias will be a vector of size 10. And because you are doing a convolution, we will see what a convolution is, but somehow you have to make these sizes comparable. So if this has 3 channels, the first dimension of the input of the kernel has to be 3, and because this has 10 outputs, the last dimension of your kernel has to be 10, and then it can have other dimensions inside. These dimensions, for instance, in this 2D convolution, will somehow be averaged during this convolution operator. So there can be dimensions that are somehow hidden during the operation, but you have to be consistent with the sizes of your operations in terms of dimensions, so that you keep some of the dimensions are fixed by the shapes of the input data and the output data. So this is the main message here. You have to be consistent from how you propagate your information through the network. They have to be consistent. They need to have consistent dimensions and consistent lengths across as it goes through the different layers. And sometimes this consistency is hard to maintain. For that, you can also have these reshaping operations, but again, the reshaping, you have these good reshapes, bad reshapes, so it is somehow difficult to keep the consistency sometimes, and to keep the geometrical meaning of the data from one to the next. Okay, so the next we have seen dense layers, linear layers. We have seen that we have to be consistent with the sizes of the different layers and weights and biases and so on. Very often the libraries help a lot in maintaining this consistency. And as we saw, if you are dealing with images, for instance, for a 512 image, then you would need in the orders of 10 to the 5 weights. So those are too many. Why don't we share those weights? So for instance, let's say that we define a kernel layer. So this kernel layer, this kernel will be the weights that all pixels will use in the same way. So the input pixels will use this 9, that is 3 times 3 kernel. So, and this pixel here is using exactly the same weight. So now you don't need 10 to the 9 pixels, not 10 to the 9, 10 to the 5 pixel weight, but you need just 9, that is 10, in the order of 10. So you have reduced your complexity, the number of coefficients that you have to compute by an order 4. So you have 10,000 fewer coefficients to determine, 10,000 times fewer coefficients. Very good. Then this is the idea of convolutional network. So sharing the weights so that all different regions of the image they use the same weight, and somehow this also gives translational invariance. So if your object of interest happens to be here in this part of the image, it will be seen some weights. If it is there in that part of the image, it will be seen exactly the same weights. So the output will be simply shifted from this region to these regions where the object is. Okay, so then very typically, because now it is much cheaper, so we have gone from hundreds of thousands of coefficients to just 9. Now you can afford to compute a few more kernels. So let's say that you have an image that is of size 32, 32 and one channel. Now what you can do is, instead of just learning one kernel of size 4 times 4, now you have you learn 8 kernels. So if you learn 8 kernels, your output images will be of size 32, 32, but now you are learning 8 kernels. You are learning on this image 8 different features, and these 8 different features, now you have 8 images, and these 8 images will propagate through the network. So the next layer is a pooling layer that we will see later, but this pooling makes these images smaller, and then you have smaller images, and then you can do the same. So now I can learn 8 kernels of size somehow 2 times 2. Now this kernel, we are learning 16 kernels, and these kernels have size 2 times 2, so it is the equivalent to this 4 times 4. But now, because we have 8 channels, these kernels that we are learning, they also have 8 channels. So the output will be this one, because we are learning 16 different kernels, and then we are doing pooling, so pooling now it is 4 times 4 times 16, and then this is 16 times 16, so this is 256. So we flatten this tensor as we saw before. So now it is a vector of size 256 components, and then we put there a fully connected layer that will produce our output. Okay, so when you have, let's say that we have an input image of this size and we have an output of this size. So then what we can do is we have defined a kernel of size 3 times 3, and now we can we can move this kernel with what is called stride 1. So stride 1 means moving the kernel 1 by 1 pixels. So you compute 1 by 1 pixels, you can compute the output of this kernel for all these pixels. So the output is well defined for these 3 pixels here, so that is why your output has 3 times 3, or is of size 3 times 3. But then you can go with stride 2. So you place your kernel here, and then instead of just moving the kernel once, you move the kernel twice. So 1 pixel and the next, and then you cannot move anymore by stride 2. So now your output will have only 2 pixels. So, and this is if we move horizontally, this is if we move vertically. So depending on what is your stride, your output can be smaller or larger, and the stride is how much we are jumping in the position of the kernels. So now we have seen that these convolutional networks, they are somehow a combination of making convolutions, so sharing the weights so that we have translational invariance to the position of the objects in the input images, and then reducing our images in a way that we will see, but these pooling layers make them smaller. So even if we don't do the pooling, so this effect that we will discuss now, that is the receptive field, is somehow exaggerated by the pooling. But even if you don't do the pooling and you think of the convolutions, so let's say that your convolutions are of size 5. So if they're of size 5, this image here, you have your horses, and then these layers here, each one of the pixels in this green image, it only sees 5 pixels in the original. And then let's say that your kernels are always of size 5, but then you think of the pixels in this layer. So the pixels in this layer, they are seeing 5 pixels in the previous layer, but each one of these 5 pixels in the previous layer is seeing 5 pixels in the previous one. So this one, in terms of the original image, each one of the pixels in the orange layer, it is seeing, if you make the count, it is 14 pixels in the input image. And then this one is seeing 40 pixels in the input image. This one is seeing 92, this one is seeing 196. And these calculations are even bigger if you think of how the pooling is behaving, because now the image is smaller, so 5 pixels in the smaller image represents many more in the original image without the pooling. So in that sense, the layers that are further in the processing, they see more parts of the image, so a bigger part of the input image. So that is called the receptive field. So each pixel here somehow receives information from a bigger area. That is what is somehow trying to represent there, and it is well described in this paper. So now you can think of multiple ways to somehow use this property. So let's say that you want to produce some images or to process some images. Now you can do it, for instance, in this way, in which the input image, this will be the output, and then the input somehow is processed in several convolutional layers. And here we have 4 layers, 3 layers, 2 layers. Each one of these layers, each one of these outputs is seeing a different part of the image, a different reception field of the image. So somehow now you can combine everything into an output layer. This one will be given the big picture, while this one is giving the details, the local details. Or you can have this skip layer net. So input image somehow feeds a first layer that is seeing only local features, but then you have multiple convolutional networks, one after the other. Each one is seeing a bigger receptive field, and then this output layer combines the information from all the intermediate layers. So this one is seeing the overall picture, and then the medium details, the low details, or the small details, and so on. And you can construct the different architecture. So in this architecture, you will provide multiple inputs, not the same input. So here we have a single input, but here you give the different versions, and then the pooling is, you don't need pooling. So somehow this network is seeing everything at the same time. Or you can have any combination of pooling, convolutions, which is seeing what, how you combine at the output. And this is actually the art of the network design. So putting just the layers one after the other is you have to be consistent with the sizes, right? It's not so difficult. But how you design the network so that the output layers are receiving the parts of the information that you are interested in is where the art is. Here we have the opposite of convolution. So convolution somehow, especially with the stride, can be seen as a downsampling operator. So we have an input, and then we will have 2 parameters. One is the stride, and the other one will be the padding. So the padding is adding some values around, typically 0 values, and these 0 values will be used to compute when you compute the convolution. And because of the stride, we have seen that the output image can be smaller than the input. So the standard convolution can perform a downsampling operator in which actually the anti-aliasing filter, if you want, is the kernel that you are trying to compute. But you can do it instead for doing downsamplings, you can do it for doing upsamplings. So the output now will be larger than the input. And the way to do that is, and this is called the transpose convolution. So the transpose convolution, you will fill a bigger image, so this bigger image, with the size that you comes from this upsampling operator. So now S is a stride. So this S is somehow used to do, if you do a stride by 2. So now you will insert a 0 between every 2 input pixels. So you will have an input pixel, then 0, and then another input pixel, and then another 0, and so on. Then you also have the concept of padding, and then you do the kernel with, or you apply your kernel to this larger image with stride prime equal 1. So this is the transposed convolution. And we will see that this idea of convolution, that is sharing weights with a kernel, can be applied in many different ways. The standard convolution one, and I don't know if I commented, no. Okay, So we will see now the formula of the standard convolution, but you can use this idea of sharing in many multiple ways. So here it is. So the standard convolution, if you look at the formula in standard signal processing books, is this one. So it is a weighted average of the neighborhood of ij, the pixel ij, and then this neighborhood that is defined between minus kh and plus kh and k as v minus kv kv, and each one of them has a different weight. So you have the input image, you multiply by some weights, and then you have the output for the coordinate ij. And yeah, so these sizes are coming from this assumption that is somehow convenient to make the presentation at the level of formulas. It is not compulsory that it has an odd number of columns and rows. So what happens if we have channels? Now if we have channels, then we add an extra summation, and then now all the pixels for the output is a combination of the input pixel at that location and all channels. So now your weights, rather than having just two-dimensional weights, you have three-dimensional weights to account for the channels. That is somehow what was represented here. So because we have three channels, these three somehow represents the fact that the kernels, so an output pixel will be using information from the three channels, and the convolution is performed in the three channels at the same time. Okay, so what is the cost of the standard convolution? How many multiplications do we need to do? So for each output pixel, we need to do number of channels in, because we are summing over all channels, and for each channel we are doing k squared, assuming that the two k's are similar. So we are doing in the order of k squared operations, and then you have to do that for all pixels, so you have to do that for all h times w pixels. So the cost of the standard convolution is of this order. Okay, now let's say that our kernel is separable. So if our kernel is separable, then we can express it, so all these weights can be expressed as a multiplication of two functions, one that depends on m, the other one depends on n. So one is horizontal, the other one is vertical. And then can be proved that this sum here can be performed in two steps. So this is a double sum. That is why the standard convolution requires k squared operations. But now here we are doing just a one-dimensional convolution. So one-dimensional convolution, the cost is k, and then this will produce a signal. So and then this is another one-dimensional convolution. So now instead of having to do k squared operations, we are doing 2k operations, and somehow it is represented here. So the first you will, to produce an output, you will produce an intermediate one-dimensional convolution, so convolution, horizontal convolution, and then you are doing the vertical convolution. So you are doing 2k rather than k squared. So now the difference is here. So and still we have the number of channels. So we have 2k and then the same cost here, and the ratio between these two is 2 over k, the cost of the standard. So the cost of separable is 2 over k, the cost of the standard. So it is much cheaper, especially for big kernels. So if you can construct separable kernels, often with all these networks, you can do whatever you want. So another way to have more convolutions, it is okay, what happens if I want to process each channel independently, so with its own kernel. So I don't want an image to be coming from all channels, but I want a channel in the output to be coming from that channel in the input. And then again, these are two-dimensional convolutions without channels. And what if I want to do a point-wise, this is called 1 times 1 convolution. So this is somehow summing over all channels. So you have an image and you have the output image, and the output image is a weighted sum of all the channels. So this is called a weighted or a point-wise 1 times 1 convolution. And 1 times 1 convolutions are very much used in many architectures. So here we have a couple of examples. So this inception network is one of the most famous ones. So we have the output coming from the previous layers, that is an input tensor, and then we are doing multiple paths. So these are paths, they're doing a 1 times 1 convolution. So it is just this weighted sum of the input layer. So if you have, for instance, at this point you have 64 images of size 64 times 64 and 192 features, then this 1 times 1 convolution is adding all the channels in a weighted way. And then you are doing the same here, you're making them images smaller, but then again combining all those networks, all these images, small images, with 1 times 1 convolution. And then here they are proper 2D convolutions. Now you take all this information, you concatenate to produce the output. Somehow this information is also here in this resonant operation, so that you have images of size 28 times 28 and you have 256 of them, 256 features that you have computed, and then what you do is you combine them using this 1 times 1 convolution. So you are collapsing everything into a single image, and then this image you are learning 3 times 3, you're applying this kernel with 3 times 3, and you do it with 64 collapses. So here actually I said you have a single image, you don't have a single image, you have 64 ways of collapsing, and then you are converting this thing to going again 256 ways of collapsing this information, and then you will have again images of size 28 times 28 to 56, and then you can put this kind of resonant information. So this what you have computed through here you will add to whatever you had before, and then this is kind of resonant block that you can put further and further. So you can also have gated convolutions. So this is the formula of the standard convolution. Now the gated convolution is almost the same, but now it is masked. So this is the pointwise multiplication, and then you are masking your convolution with something that will go between 0 and 1. And this something that is going from 0 and 1 is constructing a mask that you are also learning from the data. And somehow this mask depends on the input. So for each input, this network will produce a different mask, and then this mask is used to compute the 2D convolution. So somehow this is a kind of attention mechanism. So this network is learning where to pay attention, and then so the network learns where to focus dynamically. So dynamically means depending on the input, so that the redundant or unimportant regions are suppressed, and then you do a 2D convolution. Here is the formula for the 2D convolution. So this formula tells us is that, for instance, if we have an input tensor of this kind and an output tensor of this kind, then this is how each pixel in the channel, the output channel J, will be computed. Not each pixel, how the output channel A will be computed, and this Ni are the batches. So for every image in the batch, so this is Ni. So for every image in the batch, the output channel J, so this is a full image, will be a full bias. So this bias has the same size as the output image, plus a convolution or a sum over all input channels of the weight of that channel, and this is the input in that channel again, and then you have some weight that is a kernel convolved to deconvolved with the input. So you see, you are constructing images. So the output image is an output image plus a weighted sum of each one of the input channels weighted or convolved with these kernels. So if you want to know exactly what layer is computing, go to the documentation and you will see the formula there. What I like from this one is that it is a very nice extension of the standard 2D convolution. That is, if you study any basic course of 2D convolution of signal processing, the 2D convolution is defined in this way, but now introducing the concept of channels. So there is a convolution in each one of the channels, and all channels are combined by addition to construct the output image. And here we will see some examples. So for instance, here we have a function to simply copy some kernel values that we will be given to the weights of some layer. So actually this is interesting how the libraries are internally constructed. So here we are saying there is a layer, this layer has some weights, and these weights we will put the kernel values that you have given me. You have to interpret them as tensor because this weight is a tensor, so they need to have the same appropriate data type, and we are using the weight shape to do a reshaping of this kernel weight. So for instance, if this weight is a tensor of size 1 times 2 times 2, but you give me a 2 times 2 kernel, then this view will somehow reshape it to be 1 times 2 times 2. And then just for simplicity, we are putting the bias to 0 so that we can see just plainly the effect of the convolution. So let's say that now we have an input tensor that is this one of size 1, 2, 4, 4. So it means we have one example, one batch size. So a batch size of size 1, and then 2 channels, and each channel has 4 pixels, 4 times 4 pixels. So this is just to be able to see it properly. And then what is the standard convolution? So in the standard convolution, we are taking a layer that will be a convolution that is coming from the library conv2d, and then input of number of input channels, number of output channels, and the kernel size. And what we are doing is simply just doing the convolution. So this conv is this layer. So very often you define the layer, you keep the layer, so this is a layer, and then you apply the layer to any input tensor x. So let's say that we define the standard convolution with, so it is this class of size 2 times 2, so meaning 2 input channels, 2 output channels, and the kernel size is 2, and then we have to set the kernels. So the meaning is, as we have seen before, all the channels will be contributing to the output, and each one is using its own kernel. So we saw it here. So the kernel K is using the weight, so the channel K is using the kernel K. Okay, so we have to define what is the kernel for the output channel 1, what is the kernel for the output channel 2, and these are its kernel. And then we perform, we set this weight to this layer, and we compute the output. Okay, so we have an input tensor this here, so we compute the output, and this is the one. Okay, good. Then let's do it separable. So if we do it separable, let's see how to implement it. So we will now have two layers. One that will be the vertical convolution, and it has a number of input channels, input channels, and then the kernel size, that is 1D, and we have to group by in channels. So this means all channels are processed with the same kernel, and then the horizontal convolution, and then you see how we do it in two steps. So we have an input image, we first apply the convolution vertically, and then the output, that is called X again, we go through the horizontal 1D convolution to produce the final output. And then we define our object, we define what is the vertical kernel for input channel 1, vertical kernel for input channel 2, horizontal kernel for input channel 1 and 2. And we set the weights, and we apply the convolution. Now the result, as expected, is different. Then how, for instance, we can do this depth-wise convolution, in which each one of the kernels, they have different, each one of the, depth-wise, this one, each one of the channels is processed by the same, by different kernel. So would be this one. So this would be, and we are exploiting now these argument groups of the conv2d. So conv2d has something that says this operation has to be done for each one of these groups, and then the forward is just applying this convolution as we define it. And now we are defining what is the kernel for input channel 1, kernel for input channel 2, and this is different from what we did before, in which the kernels were for the output channels. So output channel 1 was processed in a different way as output channel 2. Now it is the input channels that are processed differently. So we set the weights, we apply, we get some results. And we can do this point-wise convolution. That was the one that we also saw here, for instance. This 1 times 1 convolution, in which the different channels are weighted differently to produce an output. So now this point-wise convolution, what we are doing is input channels, output channels, kernel size 1, and then we are putting the kernel weights. So these are the different weights of different input channels into the output channels. Very good. Now convolution 3D. So convolution 3D, the formula is exactly the same formula, but now only the tensors, the input tensors, now they have height, width, and depth. So it is x, y, z dimensions, and the output will also be x, y, z. So here the formula is the same, so that now these convolutions are three-dimensional, and they happen for every input, so for every example in the input batch. Next layers that we will see are these pooling layers. So the pooling layers is you have an input tensor, let's say, and then you have to say what is the pool size. So let's say that our input tensors are two-dimensional tensors and our pool size is 2 times 2. So that means we will divide the input tensor into groups of 2 times 2. And then this max pooling means from this group we will take the maximum value. So maximum value is 100. So all this group we will substitute by 100, and all this group we will substitute by 184, and so on. So if your input image is 4 times 4 pixels, your output image will be 2 times 2 blocks of this kind, that is 2 times 2 pixels. But now each one of these pixels represent a block. So now if you combine this idea with what I said before about the receptive field, now you see that the max pooling is, the pooling operations are actually enlarging the receptive field by factor 2 here, for instance. Another kind of pooling could be this average pooling. So average pooling would be just computing the average of the block, or you can have this LP power pool. So you take all the values in the pool, you power them to the p power, and then you do the square root of p. So this is a kind of average pooling, but now in the logarithmic space. If you set p to infinity, you get the max pooling. If you set p to 1, you get the sum pooling rather than the average. So the average is just divided by 4. So this sum pooling and average pooling would be very much related. There is another kind of pooling called adaptive pooling, but actually the adaptive is not related to the pooling operation itself, but the adaptive refers to the output size. So you fix the output size rather than the stride. So here what we are fixing is the stride. If you do adaptive pooling, what you are fixing is the output size, and the stride will be such that the input size transforms into that output size with that stride. And that is used very often to homogenize the network independently of the input sizes. Okay, then more ideas about layers are these nonlinear activations. So nonlinear activations is, we already saw the concept that you need in neural networks, you need nonlinear activation functions, so because otherwise everything would be not collapsed to a single, just one linear layer. So you have multiple possibilities, this exponential linear unit, hard shrinkage, so there are really many. All of them, if you want the exact formula, go to the documentation. But they are different ways of introducing nonlinearity into the neural network. More interesting ideas. You can have also this idea of gates, but now for the linear outputs, for the linear activation, or for the nonlinear activation. So you can have gated linear unit. So gated linear unit is I have a part that will go through a sigmoid. So this part is this part going. Where do we have it? For instance, one. Yeah, here. So we have a vector. This is a vector. So this vector goes through the nonlinear function sigma. So this vector is this one. So is this one. So it goes through the sigmoid function or whatever nonlinear activation function that you want. But then it goes one by one. So each point goes through the sigmoid, and you multiply point by point by another vector. This another vector you can also learn. So this can be given, as we did before with the gated convolution. This mask can be learned by another network. So given an input x, the input x will go through whatever network you want, and then at the end it will go through another network, and then at the end, this one will be giving kind of attention to different parts of this output, depending on the input, and then your output will be this one. So this gated linear units. More typical also kind of nonlinear functions are these softmax, that is this formula, softmin, that is this one. And this would be all for the basic layers that you can use in your networks. So see you in the next video with more sophisticated layers.